Picture this. You've spent months grinding Python. You know how to write loops, you can debug syntax in your sleep, and you've even built a few complex little apps from scratch. So you walk into the Cambridge IGCSE computer science exam feeling absolutely unstoppable. You sit down, breeze through a question about how Python code is processed, and a few months later, the results drop. You scored a 0 on that question, a surprisingly painful, completely unexpected 0. Why? Well, because knowing how to program in Python is actually entirely different from knowing the examiner's mark scheme.
So let's dive right into this painful mistake. Imagine a classic 3-mark exam question. Explain how an interpreter works. You write, it runs the code for the user. I mean, it sounds totally logical, right? That's exactly what an interpreter does. But the marks awarded? A big fat 0. This is where ordinary textbook revision just completely falls apart, because it totally ignores the rigid, incredibly specific constraints of the Cambridge examiner's mark scheme.
Here's the harsh reality the source material reveals. Generic answers will score you 0 marks in computer science, every single time. The examiner isn't looking for a casual, high-level conversation about code. They are actively hunting for precise, technical nouns and scenario-specific constraints. Honestly, if you don't use their exact vocabulary, you lose all the marks, even if your underlying logic is technically spot on. Which brings us to a really critical crossroad. In a moment, I'm going to reveal the single hidden examiner clue, a very specific command word that literally dictates whether you get full marks or absolutely nothing. But listen, if you try to use that cheat code without understanding the underlying logic, it's going to backfire. So first, we need to build the foundational framework that makes that clue super obvious. All right, Section 1, how computer languages work. To get inside the examiner's head, we first have to understand the machine itself and how it actually processes the code you write. The programming you're probably most familiar with, stuff like Python, Java, or Visual Basic, is written in what we call a high-level language. These are designed specifically to help us humans write code easily, using English-like words. But here's the kicker. Your computer's processor? It has absolutely no idea what those words mean. It only speaks pure machine code. So every high-level language requires a translator to convert that human-readable text into executable machine code. And there is a stark contrast between the two main types of translators, compilers and interpreters. This comparison is literally a goldmine for exam marks. Think about it like this. A compiler takes your entire high-level program and translates it all at once, spinning up a brand new, separate file of executable code. But an interpreter? It's a piece of software that reads your program and sends the instructions to the processor in executable form one by one. It never creates a separate executable file. That distinction, one by one versus creates a file, is exactly the phrasing the examiner is desperately looking for.
Just to quickly lock in this translation concept, let's contrast it with assembly language. Assembly is a low-level language. It's much closer to machine code, sure, but it still isn't pure binary. Because of that, it also needs translation, but it uses a highly specific piece of software called an assembler. The golden rule here is clear. Unless it's pure binary machine code, it has to be translated. Moving right along to Section 2, Python and the IDE. The crucial thing now is applying this theory to an actual programming language, in our case, Python. And to write Python efficiently, we rely on a specific environment. This perfectly illustrates why we use an integrated development environment, or an IDE, like Python's idle. Honestly, think of an IDE as a highly intelligent word processor built just for coding. It doesn't just sit there while you type. It actively coaches you. It uses color coding to differentiate variables from strings, making the syntax pop visually. It lets you run and execute the program right there in the window. And best of all, when you inevitably make a mistake, it gives you precise debugging tools to track down and fix those errors. Okay, Section 3, algorithms, flowcharts, and pseudocode. Before we even dream of booting up an IDE, we need a solid plan. We have to bridge that massive gap between abstract human thought and rigid Python code using algorithms. Let's ground this in a highly practical scenario, straight from the source material. Imagine we're building a security program. The user is prompted to input a password. If they type the exact word Neptune, the system grants access. If not, access denied. It's a super simple, everyday logical operation. We can map this logic out using pseudocode.
Now, pseudocode isn't Python, and it isn't Java. It's this fantastic, text-based, universal language that outlines the algorithm without you having to stress over the strict syntax of a real IDE. Just listen to the flow. It captures the user's input, uses basic IF, then selection logic to check if that input equals Neptune, and prints the result. It uses simple text instead of the graphical shapes you drag around in a flowchart, but it achieves the exact same structural goal.
And that brings us to Section 4, ACE, the IGCSE exam. This is our mark scheme masterclass. We are finally ready to close that curiosity loop from earlier and apply everything we've just covered directly to a high-stakes exam strategy.
The sources make it crystal clear. To consistently hit those top band marks, you have to shift from writing naturally to writing mechanically. You can literally use this 4-step answer upgrade template. Step 1, state the exact technical definition. Step 2, explain the mechanism of how it works. Step 3, and this is absolutely vital, apply the specific scenario noun from the question. Step 4, conclude with the precise examiner wording. Okay, it's time for an interactive checkpoint. Seriously, I want you to pause this explainer for a second. Listen to this question. Describe the use of an interpreter for this Python password program. Pay very close attention to the command word describe. Using our 4-step template, how exactly would you write your answer to secure every single mark? Go ahead, pause and figure out your phrasing.
All right, let's see how you did and look at the dramatic difference. Remember our generic weak answer? It runs the Python code to check the password for the user. 0 marks. Now compare that to the upgraded top band answer. The interpreter reads the high-level Python program and sends the instructions to the processor in executable form one by one without creating a file. Do you see the magic there? We use the specific scenario context, the high-level Python program. We explain the mechanism using precise terms like executable form and processor and one by one, and we totally nailed the examiner's favorite phrase without creating a file. That, right there, is how you crack the mark scheme.
But here is where things get really wild. What if the examiner changed just one single word in that prompt? What if the command word was evaluate instead of describe? Well, if you wrote that perfect top band answer we just constructed, you would instantly drop right back down to 0 marks. No way, right? But it's true. Because the word evaluate completely changes the required logic of the entire response. You can't just describe the mechanism anymore. You have to unlock a completely different framework. So, how exactly would you evaluate it? Well, I guess that's a code you'll just have to crack next time.